Hey kids, we're going to discuss torque one more time. If you understand this lesson, it'll make the next two real easy because we've already learned the important ideas. So, do this problem. Excellent job. I knew I could count on you. I always believe in you. Okay. Hopefully you know, if I have a small rock and a big rock, and I drop them both, they'll hit the ground at the same time. The mass doesn't affect falling speed due to gravity. What about rolling speed? What if I have a small ball and a large ball? Which one will roll to the bottom of a hill faster? What does it depend on? Mass? Size? Both? Neither? Tell me what you think. Okay, it's not very intuitive, so let's watch a video. This guy has two balls, one's small, one's large. I'm assuming the small one is less massive, the larger one's more massive. Which one will roll to the bottom of this plank first? They basically reach the bottom at the same time. It turns out it's not mass or radius that affects how fast something rolls. It's something else. See if you can figure out what it is. So he has two objects. This is like a metal ring. This is like a wooden cylinder. They have the same radius. And I think he set it up so that since wood is light and metal is heavy, they have the same mass. So same mass, same radius. Which of these will reach the bottom first? It was the wooden cylinder, the solid cylinder. Remember, the difference wasn't mass, and it wasn't radius. What was it? Try to explain in words. Why did the solid wood cylinder roll to the bottom faster than the hollow, empty metal hoop if the mass and radii were the same? See if you can explain it. It's not intuitive. It's not mass. It's not how radius, how far from the center it is. It's a combination. It's how far the mass is from the center. Basically, it's where the mass is distributed. If the mass is on the outside, the object will roll slower. If all the mass is on the inside, the object will roll faster, as long as they're the same size. So it's a very weird idea. It's a mass distribution. How much mass is on the outside, how much mass is on the inside. We'll hopefully make some more sense out of it. We'll see. So we learned that torque is like force for rotation. But there's a super important formula, F equals ma. Technically it's F net, but I'm running low on dry erase markers, so F is fine. We know that there must be a similar equation for torque. Force causes acceleration of masses. Torque causes angular acceleration of, well, it's not masses. And it's not mass over radius either. It's something else. Let's analyze a simple problem. Let's look at like an empty hoop that's like a hula hoop, or like a ring. Like a ring fell off your finger and rolled across the floor or whatever. A very thin ring. of mass m and radius r. Radius, again, from the center. I remember this whole thing about how the pivot point's not always the center. It is for now. The pivot point's center for a rolling object. This is a little too complicated. So instead of the whole ring of mass m, let's look at just this one little piece of the ring, and let's call it mass little m. A little tiny particle in the ring has mass m, but it's on the ring. The ring has radius r. So how far is little m from the center? It's also r. We don't want the radius of this particle. Remember, radius is not the radius of the object. It's how far from the center we're talking about. So the pivot point's in the center of the ring. It's the same radius r. And this just drew it here, except I didn't draw the whole ring. I only drew this one little piece we care about. So let's say I apply a force on this ring. The acceleration is just A equals F over F. Excellent job, me. Thanks. I know, I did a great job. How can we find the angular acceleration of this particle? We found the linear acceleration. How do we find the angular acceleration? Any ideas, Bunny? Yeah, we can just use A over R equals alpha. Yeah, we can. We discussed this equation like 2 lessons ago, last week. For any kinematics variable, A, V, D, divide by R to find the rotational equivalent. A over R equals alpha, V over R equals omega, D over R equals theta. But this is the one that's useful. So, plug in. Okay, this is fine, but we're still mixing up linear and angular. Let's get rid of this force and change to the rotational equivalent. Well, look at the ring. There's a force being applied on this end right here. So that's the force being applied on this little piece of the ring. If that force is applied on the ring, it's causing a torque. RF, well, I picked it to be perpendicular to make it easier, so torque is RF. F is tau over R. And we still got the m because there's already an m over here. So rearrange in this form. Tau is question mark alpha. Tau over Rn equals alpha R. Tau equals mr squared alpha. This mystery factor is mr squared. Mass is multiplied by acceleration to find force. Mr squared is multiplied by alpha to find torque. Technically it's net torque, but let's focus on this idea. This is like mass. It has a mass in it, but there's another factor too. The mass is not the only thing that matters. What also matters is what we saw in the video, R. How far from the center the mass is. If the mass were over here, it would be much easier to turn than it was out here. If we were in person, I could pick out like some sticks and some weights and some tape and show you more easily, but unfortunately I can't. I'll show you guys some more videos in class if I can find some. The farther from the center, the harder it is to turn. The closer to the center, the easier it is to turn. It's not just mass that tells you how hard it is to turn. It's the radius of the mass, how far the mass is from the center. This term, we'll use the symbol I. For inertia, it's called the moment of inertia. It's how hard it is to turn something. Hopefully it makes sense to you that if I have like a wheel made of lead and a wheel made of paper, it's easier to turn the paper wheel than the lead wheel. This is like a good like forearm workout. If you go to the gym, you can take like one of the plates. You don't put it on the bar. You just grab it in your hands and go back and forth like this. That'll build your forearms really well. The heavier the plate, the more better workout. But also, the bigger the plate is also a better workout, even if the mass is the same. It's more difficult to turn a larger wheel. There's a higher moment of inertia. The symbol is capital I guess M is all taken. Moment of inertia, it's a mass times a length squared. So the units are kilogram meters squared. Hopefully that makes sense. So, I equals mr squared is a formula that's not always true. It's true if you look at just one piece of the hoop, one particle on the hoop, or a particle. What if you look at the whole hoop? This is an important idea, but I'm going to go kind of fast because I felt bad because I gave you guys such a long video last time. So, if I have a hoop, if I have a bag and I put a 1 kilogram mass in and a 2 kilogram mass in, and I push the bag with some force, how do I find the acceleration? I'll divide by the total mass, 1 kilogram plus 2 kilograms. If I have a particle and then another particle and then a whole bunch of particles, how would I find the acceleration? I'll divide the torque by the total moment of inertia. If that was a little too fast, this is it. It's not too complicated. Total is just the sum, guys. If you're pushing two masses with the same force, you can add the mass to find acceleration. If you're turning two objects with the same torque, you can divide by the total I, the moment of inertia of both objects. I'll show an example that I gave on a test that will hopefully clear it up. So this is true for a particle. What about a hoop? Well, a hoop is made up of many little particles. A hoop is this piece and this piece and this piece, this piece, every single piece. All the pieces have this total mass m. So m changed to n. All the pieces have the same radius r. So I wrote a separate line. It actually comes out nicely. I use different m's just because of my example. It's the same thing. For one particle, the moment of inertia is the particle's mass times the radius squared, where r is how far the particle is from the point it's rotating around. This is kind of abstract. You don't really need to use this very much. This is a lot more straightforward. For a hoop, the moment of inertia is just the mass of the hoop times the radius of the hoop squared. A bigger hoop is harder to turn, so is a heavier hoop. M is the mass of the hoop, little m is the mass of the particle. That's why the m are different, but it's really, the formula is the mass of the object. So these are the same, but it's not always the same. What if instead of a hoop, I had a flat disc, like a plate or like a cylinder, any sort of round object with flat sides, basically just a full circle. Like instead of a hoop, a ring with a hole in the middle, there's no hole. It's just a solid disk. The nice thing is, it still depends on M and R. I'll use capital M. For some reason, they also like to use capital R in these formulas too. So I'll use capital R. I mean, I know the reason, but I don't play time. Capital R. So it does depend on M R squared. But it won't be mr squared. It'll be less. For a particle, for each little piece, little m is the mass of the particle, little r is how far that particle is from the center. So for a hoop, all the particles were distance r from the center. Hopefully that makes sense. Because here's the question. Why should the disk have a lower moment of inertia? If a hoop and a disk have the same mass and the same radius, the disk will have a lower moment of inertia. Why is that? Think about this formula. How come the disk has less inertia than a hoop? In turn, you have to explain it with this idea. Every particle has its own moment of inertia. Okay, so let me explain it again. Hopefully you can catch on if you're confused. mr squared is the moment of inertia for any piece of any object. So this piece of the hoop has inertia mr squared. This piece of the disk has inertia, moment of inertia mr squared. For a hoop, every piece has moment of inertia mr squared. So the total is just the total mass times r squared. That should make sense. And it made sense to me. And I already knew it, but hopefully it made sense. For a disk, the same thing is true. Every piece of the disk has a moment of inertia mr squared. So this piece has moment of inertia mr squared. So does this piece right here. Little m, a little bit of mass, has a moment of inertia mr squared. But look at these pictures. It's not the same r. That's why there's a difference. For the hoop, all the particles are all distance r from the center, big R. I should have called them like R1, R2, but I think little r, big R is okay. For the disk, yeah, the disk has the same radius. So all the pieces on the outside edge are at radius big R. But it's a solid disk. There's other pieces. There's a small piece right here. That's not distance big R from the center. It's distance little r from the center, and little r is less than big R. I won't go into the mathematics. It's really simple calculus if you know calculus. But it turns out, since a lot of the mass is on the outside at distance r, but some of the mass is all the way in the middle at distance 0, the average radius is what matters. Basically, the moment of inertia for a disk is not mr squared, because not all the mass is at the full distance r. it's 1/2 mr squared. Basically, you take the average radius of all the particles. The particles can be anywhere from 0 all the way to the edge. So on average, they're halfway in the middle, and that's the rate, and that's a little extra factor you put into the formula to find the moment of inertia for a disk. So let's look back at the video really fast. Oh my gosh, it was here the whole time. Amazing. Okay, so the hoop, all the mass is on the outside, but for the disk, there's a lot of mass on the inside and on the outside. The disk is easier to turn because some of the mass is on the inside, and thus the disk turns faster and rolls down the slope a little bit faster than the hoop. So there's many different objects, and they all approximately have the same moment of inertia formula, mr squared, but there's a little fraction you put on the front. I'll show the list to you right now. We only talk about a few. So I talked about a particle. If you know calculus, you could derive all of them from this formula, but if you don't, it's okay. A rod around the middle is 1/12 ml squared. If you use L instead of R, because it doesn't really have an R, it has a length. So around the middle, it's pretty low because lots of mass is in the middle. If you go around one end, which is also very common, it'll be 1/3. That's much more than 1/12. So 1/12 mr squared, 1/3 ml squared. You don't need to memorize them. If you ever needed them in a problem, you could look it up online or you'd be given a list. But those are the important ones. These are the important ones. Particle, rod, rod again. A flat, thin disk is 1/2 mr squared, as we said. Now this is a hoop. This is a disk, sorry. Hoop, disk. This is like a shell, basically a hoop, a tall hoop. This is a cylinder, basically a tall disk. So hoop is the same as, I'm sorry, shell is the same as hoop. Cylinder is the same as disk, the 1/2. I'm just looking at the first line. The other lines are more complicated, which I don't care about. And basically you skip everything else except for hollow sphere, solid sphere. A hollow sphere, since all the mass is on the edge, it's very high, but some of the mass is in the center, because the top and bottom are still in the center of the axis of rotation. So a hollow sphere is 2/3 mr squared. A solid sphere, well, a solid sphere obviously has more mass in the center, so it's 2/5, not just 2/3. You don't have to memorize the numbers. I don't know why I went over them all, but the concept is the important thing. The closer the majority of the mass is to the center, the lower I. The farther the mass is from the center, the higher I. I think I'm done with this lesson. But that's why things roll at different speed. It's not the mass, it's not the radius, it's where the mass is. It's the radius of the mass. It's how far the mass is from the pivot point or axis of rotation. You don't need to memorize them, you just need to understand the concept and know where to look online or in the book for all the values, all the equations. I'll answer your questions in class.